I start. So I introduce myself real quick. So my name is Ulrich Steinwandel, and I'm since April Flatiron Research Fellow here. And I work on a variety of problems, and from galaxy cluster scales, the largest objects in the universe, down to like dwarf galaxies. And we start with like the largest scales. This movie is not playing anymore. Okay. So what you could see in the movie on the right, can we play that again? That movie that was supposed to be on loop. Okay, great, thanks. So you can see the assembly of like a massive galaxy cluster here. So we first zoom like on a filament, and then we zoom on the most massive cluster. This is a movie that Case Wong and I did in collaboration together from like my highest resolution galaxy cluster simulation, which is actually the highest resolution galaxy cluster simulation on the market. And they're the most massive structures in the universe, like 10 to the 15 solar masses, like 90% dark matter, 10% hot volume filling gas at 10 to the 8 Kelvin. And a tiny fraction of those is like stars and galaxies. And this is like the percentage that we care about in galaxy formation. But these objects are a little bit complex, so they include a lot of tricky things like magnetic fields, anisotropic thermal conduction, physical viscosity. And this is all things that we need to take into consideration when we model these objects numerically. And they're perfect test bed for like a lot of things that contributors of the session will talk about, like RAM pressure stripping. AGNs might be of crucial importance to model these big guys. So for this, you can see talks by Ruth, Savik, and Kung for more details. And a particular interesting aspect is cosmic rays, specifically the emission. And I think this is something that Aaron will tell us more about. When we look at the other side of like the smallest things in the universe, so we reach the other end of like where I'm simulating. Can we play that movie real quick? Sorry, it should also be automatic. No. Okay, it's not playing. It's okay. So you should see here a movie playing of like there we go, a resolved dwarf galaxy simulation. So this is like the highest resolution we can do. We include single stars, supernova, resolved supernovae, photoionizing radiation, photoelectric heating, non-equilibrium cooling, like the full spectrum of feedback physics we think is important. And why should we look at dwarfs in that sense? We should look at dwarfs because they are great test bed for galaxy formation physics. So I just dubbed these like three problems that are still issues to a degree: the missing satellites problem, the cusp core problem, and the planes of satellite problem, for which all of these three problems, the dwarf galaxy population is like of paramount importance. And we will hear a little bit about detailed outflow studies in Chris' talk. Like we could also do detailed outflow studies with my simulations, but that's not what we talk about today. And then we also hear in Yingyao's talk more about quenching of local group dwarfs. And this is the journey we will take on together. Yeah, so I would like to, with this, I would like to end my introduction and ask the first speaker, Ari, to the stage. And I'm happy to take any questions in the meantime. So, yeah. Yeah. Are there questions? Sorry, I'm trying to do 2 minutes. Okay, then Ari.
Okay. I'd like to spend these few minutes talking about a project that was originated here a number of years ago called the IQ Laboratory. Highlight Jessica Starkenberg, who's the leader in putting this together and kind of making sure it continues to move on. And there's a webpage here with the information and the publications and software used for it and members list. So if you're interested in more detail, I point you to looking there. If you don't want to just ask me, if you can't find me, or more likely than not, if I'm not sure, and I point you there. So I just want to give you basically a result per paper of what this project has been focusing on. The IQ stands for isolated and quenched, and really the entire project comes from Jeremy Tinker asking a question once in a meeting, which is, are there isolated and quenched galaxies? And I don't know if we have an answer to that, but we can at least start to try to address it. In the first paper here, there was an attempt to fit the star forming sequence using Gaussian mixture models, which is a way of doing it. It's non-parameterized, unsupervised learning. And so there, you don't have to worry that we're putting in the answer we want. And you can see that in a large number of various simulations, theoretical models, we basically were able to come out with something that looks the same thing that you basically see in the data with a reasonably good fit with some spread between models. So there is a star forming sequence that one can draw in both theoretical models and in the real data. Then the second paper, Claire Dickey, tried to do a real forward modeling of this. To see if we observe the simulations the same way that observers are observing the actual galaxies in the universe, would they get similar results? And you can see overall, there's a similar trend as far as the fractions of galaxies that are quenched at given stellar mass, with some discrepancy at the higher mass end. But very interestingly, also a discrepancy at the low mass end. The insert here shows us the very low mass end. And there's a kind of common feature in all simulations that there exists always some quenched galaxies at low masses. And this is not seen in observations. The observations are upper limits, basically that at these low masses, there are no quenched galaxies. And so that's showing us something is different about simulations or theoretical models from a wide range of different models and the true universe. All right. So next, the thing that we got concerned about is dust. Dust is a real problem in trying to compare simulations into actual observations. And something that's often kind of glossed over as opposed to treated in a fair way. And Cheng Han had this very good idea to basically, instead of trying to understand dust, which is quite difficult and people have been working on for a very long time, and we still are far away from an answer, was to instead just marginalize over dust, empirically find what dust model one needs in order to make your simulations agree with the data. And so what you see here on the left side, again, showing you a bunch of different theoretical models, and the colored parts are where those galaxies and those models lie on this color luminosity plot. And the dashed lines are, again, observations. And without dust, there's huge discrepancy. The galaxies, of course, don't look anything like real galaxies. But then one could put in a dust model with free parameters and solve for the parameters that allow you to get a model that looks like the real galaxies, and therefore find out what the necessary parameters of the dust model are, and then you can then use that to make other observations. So this is an interesting framework to think about dust, and a good way to possibly deal with it if you have different situations. And finally, the last thing I'll mention is looking at gas in these simulations and comparing them to the star formation rate dependence we see on molecular gas. And what you can see here is that in the real universe, there's a fairly tight relationship between molecular gas and star formation rate. And the different theoretical models, to some extent, capture that, especially in the area where there's lots of observations. But then, particularly at the high mass end, there's quite a wide range of variations where you're not that constrained by observations between the prediction between a star formation rate and molecular gas mass. So um, again, a interesting tool for being able to understand better how our theoretical modeling should be trying to compare to the real world. I can end there.
Thank you very much, Ari. Do we have questions from the audience? Yeah, David.
Compared, I think I've asked this before about IQ data, the stuff with the Herschel data, because when you're hiding everything with or making the models fit by adding dust or changing the molecular properties, it should really show up in Herschel. And all these Sloan galaxies, we know what they look like in Herschel.
Yes, that should be done, but I think we've got to it yet.
Yeah, I think it's sort of a next step that's sort of crying out to be done.
This was my comment to Chanhan after every round of that paper, like compare to the IR data. So hopefully we will do that.
I think we have time for one more question. Yeah.
So I was just going to ask about the quench low mass galaxies in the simulation. Do you have any sense of what is the physics driving the quenching at low mass?
I would say no at this point. Yeah, I think we identified that it's happening, and it seems to identify that it's happening in some way in the different codes. But the next step of that, I think, is still to be pursued. It is strange and unexpected.
So I had the same question. My thought is, well, you identify it, and then that's clearly what's wrong with the code, and you're done. Boom. All of galaxy formation solved.
All right. Great.
Hey,
Let's thank Ari again. And Chris Carr will be next and tell us about the CGM, if I'm correct.
That's right.
Take it away.
So, hello, I'm Chris Carr. I'm a graduate student at Columbia, and I'm talking about some work I've been doing.
Can you speak closer into the microphone, please? Thank you.
Sorry, I have to constrain myself. I'm Chris Carr. I'm a graduate student at Columbia, and so this is some work I've been doing over the past year with Greg Bryant, trying to understand the supernova feedback in galaxies. And so supernova feedback is believed to be a very strong, powerful regulator of star formation, and through its ability to be able to launch gas out of galaxies and to remove the star-forming fuel. And so to try to understand feedback in galaxies, many people before us have relied on these sort of very simple, classic gas regulator models where you treat the gas mass, the stellar mass, and sometimes the CGM mass as these sort of mass bathtubs, which are fed gas through cosmic inflow. And then once it reaches the CGM, it cools and then accretes onto the galaxy, where it's then able to form stars, and then stars upon their death are able to launch the gas out of the galaxy in the form of these galactic scale winds. And so this exchange of mass and metals, which is captured by these dark arrows here, can be modeled as sink and source terms in a system of ordinary differential equations. And so once you have that system and provided some initial condition, you can solve that system and find solutions for the mass of each of these components as a function of time. And one way how we quantify the strength of these outflows is through the mass loading factor, which is shown here, which is this outflow weight out of the galaxy with respect to the star formation. And so by adjusting this mass loading factor, we can increase the amount of gas that leaves the galaxies. And this is defined the traditional approach of trying to sort of match certain galaxy scaling relations. And so here we see the stellar mass halo mass relation from Baruzzi et al. 2019. And so on the left here, we see the no feedback case where we include no galactic winds. And what you find is that we quickly run into this classic overcooling problem where we're left with an abundance of stars in the galaxies. While on the right, we include a mass loading factor that's dependent on halo mass that launches mass directly from the galaxy to the IGM. And what you see here is as we increase the mass loading factor, we begin to approach the scaling relations that revealed in the data. However, to get this agreement requires mass loading factors that can be quite large, and it's unclear whether or not these mass loadings that we're seeing are realistic or if they're plausible. So that's where we enter in with our own sort of adjustment to these gas regulator models, where we are mostly concerned with the energy regulation of the CGM. So these outflows carry, so in these models, not only are we tracking the mass flows within the model, but also the energy flows in and out of the CGM. Because these galactic outflows in their hot phase predominantly carry energy to the CGM. And so once that energy gets there, within our model, it heats the CGM. And so once the CGM is heated, it can cause the CGM to inflate. And so then a portion of the gas is sort of lifted sort of beyond the bounds of the virial radius of the halo, and that's sort of captured here at the bottom in m.cgm eject term, which sort of provides a preventative aspect of feedback in addition to the direct forms of feedback through more direct ejective means discussed earlier. And so then returning back to the stellar mass-halo mass relation, we can really see the consequences of adding this energy feedback. So on the left here, where we increase the mass loading factor, what we find quite interestingly is when the mass is being lifted directly to the CGM, it doesn't have much of effect on the resulting stellar mass-halo mass relation, because quickly that gas that you've ejected to the CGM has a tendency of accreting back onto the galaxy. And so in the end, you don't really see much of a difference. But in the case where we jack up the energy loading, we find that the stellar mass-halo mass relation is quite sensitive to our choice of A to E, and perhaps may have some dependence on the halo mass that we're interested in. And so we think this is a very interesting result that could illuminate the important roles of preventative feedback in trying to fit these certain galaxy scaling relations. So thank you.
Thank you very much, Chris, for the nice talk. Do we have questions from the audience? Yeah, Mordecai.
With your increasing energy loading, you've brought the order of magnitude down into the right range, but of course now the slope is wrong. Do you have any thoughts about where you need to go next?
Right. So what you're seeing here, these are the stellar mass-halo mass relations of a constant A to E. So a 0.1, 0.3, 0.5, and 0.7. And so what things that we have done is that you can actually fit to the stellar mass-halo mass relation and find the optimal value of A to E that actually does that fit.
As a function of mass.
Exactly. Yeah. And so for the low mass halos, you get A to E's of around 0.7, while for Milky Way like halo masses, it's more 0.1. So it allows you to make a better fit.
Highly expected. Okay, that's nice. That's kind of what you would expect physically, so that's very nice.
All right.
Thank you. Yeah.
We can take, Catherine, do you have a quick question? All right.
I noticed the red arrows going on accretion onto the gas halo and from the stars to the CGM. What about from the stars to the ISM? Can you give me physical intuition there of why there's no red arrow?
Oh, so why don't we include a red arrow from the stars that could be heating the ISM? Is that what you mean? Right. So for this model, we're more interested in the energy regulation of the CGM, but of course there would be other arrows that would be in between the ISM and the stars. But this model was more concerned with the CGM. But of course that would be a present.
Great. Then let's thank Chris again, and we move on to Ruth Daly, who will talk about the outflow method for measuring black hole spin. take it away, Ruth.
All right. I have been working for some time on developing new methods to measure how rapidly black holes are spinning. And I've been settled on a model which I call the outflow model, which is based on the outflow properties of sources. So I'll show you some evidence in a minute that suggests that these powerful outflows are powered by black hole spin, which has long been thought to be the origin of the outflows. The samples I'll be talking about include, this pointer work? Well, include 100 FR2 sources, 576 liners, 80 local Seaford and liner galaxies, and 102 measurements of 4 X-ray binaries, where those measurements are simultaneous in radio and X-ray. The key empirical ingredients that go into determining the black hole spin in this picture are the beam power of the outflow, denoted here as L sub J, which is determined using the strong shock method and the fundamental line mapping method. The bolometric accretion disk luminosity, which is obtained with 2 well-established methods for different samples. And the black hole mass, which is also determined with well-established methods. Using those empirically determined ingredients, we found, myself and 2 undergraduate students in 2018, that all 4 samples, is there a pointer? It is showing, thank you. I think if you just move it around, it shows. Okay, so all 4 samples shown here in different colors independently line up on this diagram where I'm plotting the beam power over the bolometric luminosity of the disk versus the bolometric luminosity of the disk in Eddington units. So these 4 completely different samples have the same slope and the same normalization here. And I take that to mean that they're all governed by the same physical process. Some of these sources, such as those up here, have beam powers 100 times larger than the bolometric or radiant luminosity of the disk, suggesting these must be spin-powered outflows. And since they all have the same relationship here, I argue that means that they're all, at least in part, powered by black hole spin. This relationship parameterizes the empirical result here, and note that there's no accretion disk model assumed, and there's no specific jet formation model assumed either. Everything on this diagram is empirically determined. So to summarize a lot of work in just a few lines, what I do is I took the empirically determined relationship, which can be written in this form, and looked at the theoretically predicted functional form for a spin-powered outflow. The functional form for a spin-powered outflow applies whether the outflow is powered in part or in full by black hole spin. For example, the Meyer model in 1999 has a substantial amount of the beam power being powered by the wind from the disk, but it also includes a spin-powered outflow. All of these models have the same functional form, shown here in black, same as the Blanford-Zinyaik mechanism and other spin-powered mechanisms. The thing that's different from model to model is the coefficient, the constant of proportionality here. What I showed in 2019 is that we can recast this theoretical equation in what I call dimensionless separable form, where we rewrite it so that it separates into a piece that's just the outflow, a piece that's just the disk, and a piece that's just the black hole spin. Then you can identify terms between the theoretical equation and the empirically determined equation and solve for lots of quantities. Here, I'll be talking about black hole spin, and I only have one more slide. But you can solve for the magnetic field strength that is anchored in the disk and is threading the hole. You can solve for that in dimensionless units and in physical units. And you can also solve for the mass accretion rate, which I'm not going to talk about today, and the black hole spin. I'll just go to a summary slide of what the results are. The main result is that the black hole spin is unrelated to AGN type. So I already had found that in 2016 using the just the FR2s. You could see that the high excitation galaxies, the low excitation galaxies, and the quasars all had very similar spins, although they're very different in type. And this turns out to be the case for the other types of AGNs, the liners, the Seifert and liner galaxies are local, and also the X-ray binaries. The next key point is that there's very good agreement between values determined with this method and values obtained with other methods that have nothing to do with the outflow and don't include the outflow properties at all. So for example, there were 6 AGN that could be compared with the results obtained with the X-ray reflection method, and there's very good agreement there. Same for one of the galactic black hole systems, the X-ray binary 3C339-4. The outflow method gives a result with very high precision and excellent agreement with that obtained with the X-ray K-alpha iron line method. And now there's a new paper out by Mojigan et al. 2020 into 2021, and they use the continuum fitting method applied to many 3CR sources. 15 overlap with mine, and that's also excellent agreement. Again, their method, the continuum fitting method, has nothing to do with the outflow and does not include any outflow properties at all. I'd like to emphasize that the method and results are all empirically based. So this might be able to be used to study and constrain the accretion disk models that would fit these results, and also disk jet formation models. Finally, there are 3 empirical indications that the outflows are powered by the black hole spin. The accretion disk physical magnetic field strengths agree with those obtained in the context of specific accretion disk models for the same sources, and those specific accretion disk models do not include any information regarding the outflow properties. Same for the mass accretion rates and radiant efficiency factors obtained with the outflow method agree with those obtained for the same sources using models that have nothing to do with the outflow. And finally, there are many sources with outflow beam powers in erg per second that are 10 to 100 times the bolometric luminosity of the disk, arguing, again, as many people have argued, that indicates the outflows are spin powered. Thanks.
Thank you very much, Ruth. I think we have time for one quick question. Is there a question from the audience? Then I ask a quick. Mordecai has a question. Yeah, Mordecai. Sorry? Okay. So for me as a simulator, that means I should put that in my models, right?
Well, or absolutely, or you could look at it the other way around, right? What types of... Oh. Yes, we should definitely talk. No, I think also what this means is you could take the results that I've obtained and ask what accretion disk models will give you the mass accretion rate I'm obtaining, will give you the magnetic field strength I'm obtaining. Well, in other words, you have to have the whole package, and I think it would be very interesting to see if there are some simulations that would give these same results.
All right, Mordecai, you want to ask yours? No? Okay. A quick one, Rachel.
May just be terminology. When you say spin powered, is that the same as Lanford-Genaic or something else?
Can I go back at all on these slides?
The small button.
Oh, thank you. Yeah. It's all spin powered outflows. So the Blanford and Genaic mechanism. I think that here we go. Has this equation here. The beam power goes as the colloidal component of the field squared times the mass squared times the spin function squared. All other spin powered outflow models that I have looked at, and I've looked at 4 or 5, every one that I could find that had an analytic expression, they all have the exact same relationship. The thing that's different is the constant of proportionality.
Okay.
We actually determine that empirically, and the model that matches is the Meyer 1999 model. However, as I say in my 2019 paper where that is discussed, it's still early days, and there could be some shifts and normalizations and other things. So I'm saying I was happy that a model matched, but it doesn't mean at this point that that is the correct model or the only mechanism that's working in all sources with outflows.
All right.
Thank you,
think,
Ruth.
I think we have to move on to the next speaker, Savik. Yeah, thank you very much, Ruth, again. Sorry.
Okay, so I will try to cover sort of think of this as a teaser. And I'm putting up a photo, obviously pre-pandemic, of a group meeting that we have, including Mordecai, who's here, and Barry and Jillian, and quite a number of students on Friday morning. So if you're really interested and want to talk to us some more, we meet on at 10 a.m. on Friday mornings. And I'm going to be talking to you about the AGN channel for binary black hole mergers. So I wasn't really sure where to put this talk, so I said galaxies, because I am going to be talking about active galactic nuclei. And so just a reminder for folks who haven't heard me talk about this before ad nauseum, on the left, we have a picture of our nearest galactic nucleus, and you can see all of the orbits of the S stars. Of course, Sagittarius A star is not currently an active galaxy, but if it were, we would expect that the size of the accretion disk would be around 0.1 or possibly up to 1 arc second. And so you can see from the scale on this image that the pericenters of the orbits of all of these stars would intersect with the AGN disk, or in fact, the entire orbits in some cases. We also expect that in the centers of galaxies, there should be a very dense population of stellar mass black holes from both theoretical and observational evidence, about 10 to the 4 stellar mass black holes per cubic parsec. So there should be quite a few in this image, even though we don't see them. And they arrive from the decay of globular clusters, minor mergers, local star formation, etc. So if you take that idea seriously and you apply some protoplanetary disk migration theory, you can figure out that these black holes will move around in that disk and they will meet each other and they will form binaries. And when black holes form binaries, they have this really convenient property that they emit gravitational waves, which are detectable, of course, by LIGO. And so these black hole binaries, if they're forming in AGN disks, are actually a probe of the midplane conditions of AGN disks. And you can also learn quite a number of other things about the parameters of and conditions inside of AGN disks. They also have another convenient property that if you have a binary black hole and it's merging in an AGN disk, it's merging in the presence of matter. And so you have a hope of having an electromagnetic counterpart, unlike any of the other channels. And so I'm just trying to like sum up a bunch of different things here, but this is a figure from the most massive, highest probability LIGO detection, GW 190521, which had the 2 ingoing black holes are both massive enough that they should be in what's called the para-instability supernova mass gap. So the stellar mass modelers can't make them directly from gravitational collapse. And the simplest explanation for why they are that massive is because they are the result of a merger of a prior generation of black holes. So if they are the merger of a prior generation of black holes, then this is at least a 2nd generation merger. But black holes take a really long time to merge under only gravitational wave emission. You can take a 10 solar mass black hole and a 15 solar mass black hole and put them 4 AU apart, and you will be waiting 10 to the 5 Hubble times for them to merge. So as you all know, space is very big. You have to get them very, very close together. So you need to do this in some kind of very dense environment, like a galactic nucleus. There's a further complication. If you merge a couple of black holes and they have any spin on them to start with, they will get a kick. and they will be, that kick velocity is typically at least 50 kilometers a second. So the other location where you can have high densities of stellar mass black holes are in the cores of globular clusters, and they have escape velocities that are less than 50 kilometers a second. So you don't get to do it twice, or certainly not 3 times, 4 times, to get up to these relatively high masses. So depending on what you think the upper mass is for a black hole from direct collapse, from directly from star formation, you start to get have a very hard time creating things as massive as GW 190521. And so I would argue, independent of anything else, that this being extremely massive with what's looking like an upper mass cutoff, maybe actually closer to 35 solar masses from the most recent LIGO data release, that this is a 3rd or 4th generation merger that cannot be made anywhere other than a galactic nucleus. And in my next slide, I will argue that if you accept that argument, then it also actually has to come from an active galactic nucleus. There's also an interesting, but I will still say, I'm still going to call this a candidate counterpart. I'm not betting my kids' college fund on this, but it is very interesting that there is both a spatial and temporal coincidence with a flare in an AGN from ZTF, observed in ZTF, that was coincident with the 1905-21 detection from the gravitational waves. And so to just flesh out a little bit why I think that why high mass gravitational wave sources have to be from AGN if they come from a galactic nucleus. I've already explained that you have to have a very deep potential well. Certainly, if you want to get over 3rd generation mergers, depending on the characteristics of those mergers and the characteristics of black holes, if they have identically zero spin or just low spin, you may be able to make 2nd and occasionally 3rd generation mergers in globular clusters. But the other thing that you have to bear in mind is, although quiescent galactic nuclei are more common than active galactic nuclei, quiescent galactic nuclei have very different dynamical environments. And so in quiescent galactic nuclei, although you can make a lot of binaries, you tend to break them up as well because they are dynamically hot. In AGN, on the other hand, you have a cooling environment where you form binaries and you can bring them together and harden them past the hard-soft limit and allow them to merge in very short timescales. And so if you say that, then you can decide what fraction of the mergers that come from galactic nuclei might come from active or quiescent. And depending on the lifetime of an AGN disk and what fraction of galactic nuclei you're going to count as active, that have this dynamical cooling effect, the blue regions of parameter space are where the AGN win. The red regions of parameter space are where the bare nuclear star clusters might win. So it's only for very, very long-lived AGN disks. And if you accept that 1905-21 was from an AGN, then somewhere between 25 and 80% of all of the LIGO mergers are actually coming from AGN. That's me.
Thank you very much. Do we have questions from the audience? One quick question. Rachel?
So my impression is that there are very few binary observational signatures of binary black holes in AGN. Is that still correct? And how does that sort of fit with your picture?
So do you mean that from among the observational signatures that we have from the gravitational wave detections that not many?
No, I'm talking about like optical. So I'm thinking of like Julie Comerford's work or Dan Stern's work, where they've looked at AGN to try to see if they can see signatures of a binary being in the AGN.
Oh, sorry. Really important. So LIGO detects stellar mass black holes. So these are stellar mass binary black holes that are forming a binary in the AGN disk. And so it's very hard to see them in any kind of electromagnetic signal.
Okay.
Except if you have something that's specific to the moment of merger, because if you figure, even if they're extremely super Eddington, they're 10 to the 6 times smaller than the central object.
They're just too faint.
At 1% Eddington.
Okay.
it's a losing battle. So you have to do some fancy work to get an electromagnetic signature that's observable of these binaries. But no, you're right. Seeing actual, and it's actually very non-trivial to find supermassive black hole binaries in the electromagnetic regime as well. And I have some work and thoughts on that if you want to chat later. It's
All right.
it's one of those absence of evidence is not evidence.
I think we should
Good.
move on.
Let's chat later.
And
Thanks.
Rachel and
Thank you.
Savik can chat later. So our next speaker will be Shai Gennel. Let's thank Savik again. Thank you very much. Will be Shai Gennel, and he will talk about a new morphokinematic classification of massive ETGs. Shai, take it away.
Thank you. Good afternoon. So I'm a research scientist here at CCA and also an adjunct research scientist at Columbia. Generally, I study galaxy formation using large-scale hydrodynamic cosmological simulations. I've been in the core development team of projects like Illustris back then and Camels these days. But today I want to tell you about one specific project that was led by an undergrad student at Columbia that I worked with together with Greg Bryan over the past year and a half. So this is Sahil Hegde, and he actually just started grad school at UCLA this fall. And in this project, we looked at massive elliptical early type galaxies in the TNG 300 simulation and tried to do two things. So one is classify these galaxies. Classify these galaxies in new ways. So what you see here in the bottom right is the usual way of classifying the kinematics and shapes of galaxies. On the y-axis, we have the spin parameter, on the x-axis, the ellipticity, and we see in blue, blue and green, these fast rotators, and in red, the slow rotators. That's like the general classification of these massive galaxies. And we wanted to, but there are many more interesting features like kinematically decoupled cores and misalignments and stuff like that. So we wanted to go in more detail. The other thing is we wanted to drill down specifically on this interesting population that only constitutes a few % of the massive galaxies, which are prolate rotators. So what are those? So you can see these in the bottom left here. So we see here the image of an actual observed galaxy and its kinematic maps. And what you see is it's elongated along this dashed line, but its rotation, so its velocity, projected velocity gradient goes perpendicular to that. And that's as opposed to what disks look like. And it's just an example of a classic disk where these two, this elongation and the velocity gradient are parallel. So this is disk rotation. This means that in this galaxy, in the prolate rotator galaxy, the stars are rotating around the major axis. We tried to understand the origin of this phenomenon. So we started by asking how stable are these kinematic axes, and we actually found something we didn't quite expect, that they're not so stable in the majority of these galaxies. So we defined this quantity, the reorientation rate of these two axes, the major axis, morphological axis, and the kinematic and the angular momentum. Reorientation rate, simply the degrees per gigayear, how this vector is moving in 3D space. And here in the top right, we show just these two reorientation rates against each other of the major axis on the y axis and of the angular momentum on the bottom. And so together with the misalignment between these two axes, we defined these 6 different classes of galaxies. And I want to show you some poster childs from a few of them. So in blue, we see these what we call the twirling cigar. This is like a bar rotating inside this galaxy. So we have high reorientation rate of the major axis because it's just rotating around like this, but the angular momentum axis is is fixed in space. Then we have in purple these prolate rotator galaxies where both axes actually fixed in space, but the misalignment is such that the rotation is this misalignment angle is about 90 degrees, so the rotation is around the major axis. And then we have the yellow galaxies which are kind of the morphological axis. Their shape is fixed in space, but actually their angular momentum jumps all around, and we didn't quite expect that. So we called them the rapid angular momentum reorienters. Okay, and then we went and looked at the formation histories of these different classes with a particular focus, which is what I want to tell you about now, on these prolate rotator galaxies whose origins is a bit mysterious. And what we find, first of all, is that these 6 new classes we define of galaxies are fairly stable over time. So if you find a galaxy in a certain class, it's usually going to be in the same class a few gigayears before or after, pending major mergers. So it's usually major mergers that really place these galaxies into their, so the most recent major merger put this galaxy in its present class. And then specifically thinking about prolate rotators, we identified, so this is a poster child of kind of the last major merger that gave rise to one of those prolate rotators. And really the key moment is this final infall that you see on the top right. So we see the first progenitor and angular momentum pointing horizontally. You see the velocity field. And then we have the satellite falling on an almost radial orbit that's parallel to the angular momentum of the galaxy. And the result, the descendant galaxy, essentially has been stretched along the direction of the angular momentum of the progenitor. So the key point here is that this configuration, what really controls the result is the configuration of the merger at this final infall moment. And we could not find a direct connection to the orbit of the merger or the configuration of the merger in general, at the very radius. So it's really the dynamics that's going on just before this final infall or during the first approach that determines the final configuration of the merger and the properties of the descendant.
Thank you very much, Shai. Do we have questions from the audience? Yeah, Julian.
This is a wide range of gas fractions, actually. Yeah. What does make a difference is that the first progenitor actually needs to have a lot of angular momentum. So usually those are these galaxies essentially hit, through their minor axis.
Ari?
What's the statistics on this? I mean, how rare is this kind of thing? Or your different classes in general?
So these both in the simulation and in surveys are a few percent of the population. It's a mass dependent statement. So didn't go into detail if there's an exact match here of the simulation, but generally speaking, a few percent of the massive. So we focused here on 10 to the 11 solar masses in stars and above. So really massive galaxies.
All right. Thank you, Shai. I have a question for you, but I will take that offline.
Okay.
And let's thank Shai again. And our next speaker is Festa. Is that correct? Yes, that's correct. Okay. Take it away. It's a big button. Yeah.
Good afternoon, everyone. My name is Festa. I'm a graduate student at CUNY. I've recently joined the CUNY Astro community only this semester. I'm working with Viviana and Ari. And the question we've been trying to investigate these past couple of months is whether we can predict galaxy sizes from halo properties and whether we can, in a way, use machine learning tools to answer also this kind of question. So we have focused on SIMBA simulation, specifically on the central galaxies in SIMBA. And here on the left plot, we can see that there is a strong correlation between size and mass, which is something already known. So we wonder whether we can explain the scatter in this kind of relation better. And in the right plot, we try to see the relation between angular momentum and size, as we know that in literature, most of the time, angular momentum is considered an important factor that predicts galaxy size. However, in sim-based simulation, it seems like there's a weaker correlation between angular momentum and size. So next, we look at correlations between physical properties of galaxies. Here, if we follow from left to right, the first column, we have size, and then the upper rows are the correlations of size to the other 7 galaxy properties. The next one is galaxy mass, followed by halo mass, and then bulge over, total mass ratio, instantaneous star formation, stellar age, gas fraction, and angular momentum. I would like to use a pointer, but I'm not sure. Okay. Okay, then yeah, from left to right, we go with size, and then galaxy mass, and then halo mass, bulge over total mass, instantaneous star formation, stellar age, gas fraction, and galaxy angular momentum. So we see that there is some correlation between most of these properties. However, the correlations seem kind of complicated, and we ask whether we can use machine learning tools to disentangle this problem. So as a first step, we look at 3 different cases. The leftmost plot, we have a linear model here where we use only galaxy mass to predict galaxy size. And we see that that is not enough. So galaxy mass is not enough to predict galaxy size. So as a next step, here we use all of the previously mentioned features, so all of the previously mentioned galaxy properties, to see whether we can predict galaxy size. On the y-axis of all of these 3 plots, you can see the predicted value of galaxy size, while on the x-axis are the true value of galaxy size. And we see that this kind of model is better. When we use all the features, we do a better job. However, if we use a machine learning model, this becomes even better. So a machine learning model can help us really to capture better the relation between galaxy characteristics and size. Thank you.
Thank you very much. Do you have any questions? Yes.
I guess my question is, do you know how many parameters you can get away with predicting, like having a good prediction? Or are they like all very important, or like you can just use a couple?
Yes, so that's what we're trying to do. So with the random forest model, we can extract which features are most important in predicting. So that's our step that we're working on right now. As for the number of features, I mean, we're still not sure how many features we should use right now.
All right, then let's thank Vesta again, and Kung Yi will be the next speaker. He will tell us about how AGN outflows work.
Hello everyone, I'm Kong. Hello everyone, I'm Kong Isu, a joint postdoc in Columbia and CCA. So I'm going to talk about various projects regarding AGN feedback in different scale that I did and also am currently doing. So a few months ago, we published a paper that surveying a wide parameter space of AGN jet model in 10 to the 14 isolated galaxy simulations. So we want to test like a wide variety of AGN jet model and see whether any of them could quench the galaxy and solve the cooling flow problem. So we test jet with constant energy flux of different sort, like thermal, kinetic, cosmic ray, magnetic energy, and also different other jet parameters like jet width, jet precession, and duty cycle. So, and this is a cartoon that we put in paper that's nicely made by the graphic designer Lucy in CCA. And yeah, so except for that, the energy of the jet should be correct. Also, that we found that a more important criteria of that is that the the cocoon inflated by the jet should have long enough cooling time at the cooling radius, and also the width of the cocoon have to be wide enough at the cooling radius. So these are the criteria for a model to be more successful in the galaxy scale that could more stably quench the galaxies. Also, so to fulfill this criteria, we found that you either need a hot thermal jet or a cosmic ray jet or a very wide kinetic jet. So these movies are example of the cosmic ray jet. We found that be more successful. So following that work, we are also doing like surveying these more successful model in different halo mass from 10 to 12, 10 to 15 solar mass. In this work, we found that it seems that energy, the required energy to quench in different cases will roughly scale as the free fall energy at the cooling radius, and also cosmic ray jet in all cases will suppress the cooling flow and quench more efficiently. So beside this, we further would like to narrow down the more successful jet model by doing multi-phase comparison to the observations. So as an example, these are an X-ray image of a more heavier galaxy, 10 to 15 solar mass galaxy with cosmic ray jet, and the right-hand side is the H alpha image. And also, we're trying to include live accretion and see whether any of them could like consistently self-regulate quench the galaxy. So these are all ongoing work and preliminary. So beside the galaxy scale, we also have a set of works that try to zoom into the black hole neighborhood and see down to the radius that we actually resolve the individual capture of the gas particles to the black hole. So we don't need a more subgrid accretion models, and want to see how different feedback, how agent jet could affect the black hole accretion and in that scale. So yeah, so we test different agent jet model, and also varies so this is a patch of gas with constant density and temperature, and we also around a black hole, so we varies the gas density and temperature, and also the jet model, and also the feedback efficiency. So for example, these are a set of runs that we did with 100 solar mass black hole in a primordial gas. So this is the patch of gas with like 200 milliparsec box around the 100 solar mass black hole. So if I play the movie, you can see that these are like the case that we systematically varies the background temperature of the surrounding of the black hole, and you can see that things with various temperature, it also significantly affects the size of the Bondi radius, and you see that the regulations will roughly happens at a radius like roughly comparable to the Bondi radius. So with the lower temperature, the Bondi radius is much larger, and you see that the jet does reach much larger radius, whereas the higher temperature cases, the regulation happen at a very small scale, again roughly at a Bondi radius scale. So another thing interesting we're still seeing and also found is that found that the propagation of the jet along the jet direction is actually governed by the momentum conservation, and also in the radial direction is more governed by the energy pushed by the energy of the jet. And as you see, if at we said that the regulations happen at Bondi radius, if at the radius the radial motion is much larger, then the jet cocoon become a more energy-driven bubble, whereas in the other case where the jet direction is much faster than the radial direction, it become more momentum-driven cocoon. And as you can see, when we vary the background density from 10 to 2 to 10 to 6 particle cubic centimeter, the lower the density is, the more like a bubble it is, and the higher density it become a more elongated cocoon. And also similar things, we can also see that when we vary the jet velocity, the lower the jet velocity is, the higher the momentum flux is, and actually you see that it's a more elongated cocoon, whereas for the higher temperature, for the higher velocity case, it's more like a energy-driven bubble. So these are all ongoing works, and we'll have much more result in the future months. So stay tuned for.
Thank you very much, Kung-Yi. Questions from the audience? Yes.
So you said it, I think on your first slide, that you were finding that you can find the duty cycle from your simulations, and I'm wondering what sorts of ranges are you finding for that?
So for the first, could I go back? So for these, these are actually constant flux jets. So I actually put in different duty cycles.
Oh,
so those
okay.
are not.
Sorry, so that's
those are not. So yeah, we'll have more handle on that for those live accretion things. Where
do some duty cycles work better than others?
So we found that if the duty cycle is much smaller than then like the cooling time, dynamical time, the cooling radius is effectively like a continuous jet. It doesn't actually vary so much. But for the longer side, it will effectively lower the efficiency of the quenching of the cooling flow and also the star formation.
Cool. Thanks.
Great. Thank you very much, Kungi. And we move on to our next speaker, Aaron Tran, who will tell us about diffuse radio emission in galaxy clusters. Take it away, Aaron.
Okay, thank you. Hey, everyone. Okay, good. Hi, everyone. It's great to be here. I want to tell you a little bit about a project I'm doing with Lorenzo Cerrone at Columbia. I'm a graduate student. I like to joke that of his group, which does a lot of high energy stuff, fast radio bursts, gamma ray bursts, and things like that, I'm the lowest energy person there. So let me tell you a little bit about that. So the idea is if you look at a galaxy cluster, let me see, how do you do the thing? Whatever. Okay, if you look in the right side of the slide, you see a lot of diffuse radio emission. You see injection of relativistic electrons directly from, say, radio galaxies. You look at galaxy cluster merger, you might see kind of like very large elongated red-like shocks in the outskirts. And oftentimes you'll also see kind of like diffuse halo emission within these clusters. And one thing that they kind of have in common is that we can't rely only on direct injection from the galaxies and shocks, but rather it's been postulated that there should be some population kind of fossil electrons that are kind of floating around. They're generally invisible. They're relativistic in energy, but not quite relativistic enough to emit synchrotron at the megahertz to gigahertz range. And so one question is sort of, well, okay, we have these electrons floating around down here. You only need to kick them up by maybe a factor of 10 or 100 in energy to get them to emit again and maybe help explain some of the radio emission that we see. How do we do that? And one idea is that because these guys are kind of in a sweet spot and the cooling is a function of their energy, they can kind of sit around for of order, one, they sit around for of order Hubble time, and two, because they have a gamma factor of order 10s to hundreds or so, they might kind of be in the right regime to gyro resonate with waves driven from thermal ions. Okay, so this is a generic property of high beta plasmas. When I say high beta, I mean a plasma that has a high thermal pressure relative to its magnetic pressure. You kind of squish it or you dilate it a little bit, erupts in waves very quickly, and it regulates back down to keep the plasma isotropic. And so we see that in the solar wind on the left. At a low beta, where it's well magnetized, you kind of have excursions of temperature and isotropy to larger values. But as you move towards a higher beta, hotter plasma, weaker magnetic field, you see that maintains isotropy pretty well. And this is true of the intracluster medium as well. So I can go ahead and play a video. Here's one showing kind of what happens if we squish a plasma in something like ICM conditions. What we see as a dominant instability is a sort of mirror instability, these kind of static regions. Let me try to play it again. Okay. Yeah, these kind of static regions of low field and high field. But underlying that, there's also subdominant ion cyclotron instability. And this is the one of interest to us. This is a left circulated polarized wave. Because of the fact that these fossil electrons might gyro resonate with it, it could be kind of, more effective at scattering particles and damping, giving some energy to these cosmic rays. So our strategy right now, we're kind of focusing on 1D to isolate this gyro resonance. You can see in the top kind of a box showing what we're doing. We have a domain along the magnetic field, and we can measure, define in an appropriate way, a fractional energy gain as a function of the input cosmic ray energy. In the regime that we're considering, the energy density of cosmic rays is very low. We treat them as test particles. And we can kind of see a lot of structure as a function of time. As you squish the plasma more and more, first the low energy cosmic rays gain some energy, and slowly the rest of the higher cosmic rays also start to gain energy. I won't go into the details in the interest of time, but I'll put up some results here. The basic idea is that so far it's basically dominated by pitch angle scattering. You can think of it as if you squish the plasma, because of this efficient scattering, the cosmic rays is something like an effective gamma of 5/3, or maybe a bit less. That's shown by the black line in the middle plot. And if you kind of decompress down under the ad hoc assumption that, well, let's not scatter anymore, this plot in the middle and on the left kind of shows what fractional energy you would keep in that process. Right now we're in the process of kind of disentangling different families of waves, whether, resonant versus non-resonant scattering is more important. But I think I'll just leave it there and happy to take questions. Thanks.
Thank you very much, Aaron. Let's take one quick question from the audience. Is there a question? Yeah, Mordecai.
Oh, this was a one-dimensional model. If you squeeze at an angle or even perpendicular to the field lines, I assume you're squeezing along the field lines here. Do you think you're going to get similar or very different results?
Well, right now, so I should say we're not squeezing along the field line, we're squeezing perpendicular to it.
Okay, then rotate my question 90 degrees.
Yeah, so in this case, well, the mechanism is flux freezing basically to drive the anisotropy. We're going to squeeze along it. It's not entirely obvious to me what would happen. Perhaps you get, beam instability, spiral hose modes from driving a different anisotropy.
All right, thank you, Aaron. I also have a ton of questions for you, but I will take my questions offline. And then let's move on to our last speaker of the session, Yinghao Su. Is that correct? Yes, I think that's correct. Last speaker. Yeah. Yeah. Let's thank Aaron again. Sorry. And Yinghao, take it away.
Yeah, I really want to learn how to use this one first. All right, that seems good. Big button is right. All right. Hi everyone, my name is Jing Yao. I'm a second-year PhD student at Columbia. This is on my work with my advisor Mary Pittman on the smallest galaxies in the world. And so the motivation of this work is kind of start locally in a local group. So we found that this picture is by Mary and collaborators. Oops. My cursor? Okay, over there. So this is a snapshot of galaxies in the local group. The two big black circles are the Milky Way and M31. These are two big spiral galaxies. And the gray elliptical line is model local group surface. And the dots are the scattered dwarf galaxies in the local group. So you can see the blue dots are the more isolated ones. These have H1 detection, so these are not gas quenched or still star forming. And the red ones, they tend to be more embedded in the host galaxy's dark matter halo or in the local group medium, and they tend to be H1 deficient or be gas quenched. So if we think about some potential mechanism this might be happening. So we think that the ram pressure of local group medium or the host medium might be stripping the dwarf galaxy's gas content. The question to ask is this picture unique to the local group, that is to Milky Way and M31? In particular, the SAGA survey of recent years that uses the Sloan data of galaxies, they found, so the picture on the right, they found a discrepancy of the quench fraction in the y-axis there from the Milky Way. So the Milky Way has a high quench fraction of about 0.8, whereas the SAGA galaxies had only about 15% of quench fractions. Most of them are still star forming. And our work is looking at the local universe, so about 2 to 10 megaparsec. That is only because of our H1 resolution. We will extend that to a larger volume when future data is available. In particular, we're using the alfalfa radial H1 21 centimeter H1 catalog to look at local spiral galaxies and their dwarf galaxy population. This is what we found. So we found a bunch of local spiral galaxies in 2 to 10 megaparsec. These are called our our primary list. And we see a large diversity of range in their mass and environment. So these are not entirely Milky Way analogs. We have some smaller ones. The circles are their projected virial radius on the sky, and the dots are our satellite list. These are obtained from a combined spatial and kinematic selection, so they're very close in projected radius and velocity to their hosts. So I do want to point out that our satellite population is the gaseous population only. So these are considered the star forming or the non-quenched population. All right, if I put all my galaxies to the perspective of different hosts, different spirals, I have a picture like that. So on the x-axis, I have the size of the host galaxy, dark matter halo mass, and the blue points are the alfalfa spirals I just showed you. And on the y-axis, we have the number of gas-containing or the non-quenched satellite number. So compared to the local groups, so compared to Milky Way and M31, we seem to find some consistency in the observed number, low number or high quenching effectiveness in the 0 to 2 low gaseous dwarf number. There is a very weak trend of host mass dependence, so the lower, the very small spiral hosts tend to have 0 satellites. And in comparison with the Saga catalog, so they're known to be very star forming, tend to be star forming or non-quenched. But after we made the correction, take out the brightest satellites for consistency with the local group, then we see that the number goes down drastically and it's still in fair consistency with Milky Way and Andromeda. And finally, the gray points that are cosmological simulations of Auriga galaxies. We have a suite of 30 halos simulated Milky Way analogs. They have a slightly higher satellite number, but we already found that the satellite definition, or how bright these are, how bright we apply the cuts are definitely very important. So we haven't corrected for the massive satellites yet, and we do expect to see the numbers to go down maybe to be more consistent with the observed ones. So one takeaway from our work is there might be some universal quenching mechanism that's effectively stripping the dwarf galaxy's gas content by these spiral host galaxies. Thank you, that's all. I'll take any questions.
Thank you very much. Let's take questions from the audience. Yes, Alison.
You keep saying that you're correcting for the massive satellites. Does that mean things like the Magellanic Cloud type?
Yes,
Is that what you mean?
that's a great question. For the Milky Way or Andromeda population, we're including up to the LMC and SMC masses, but we are excluding like M33 triangulum galaxy.
Okay.
Masses. So in terms of stellar mass or rotation velocity, that's the largest in our sample is about 90. That's considered a dwarf satellite, but M33 is like 120 or 130. That's excluded.
Okay, thank you.
Yep.